The third axiom of probability tells us that the probability of the union of two disjoint sets A and B is the sum of the individual probabilities. Now, what if A and B are not disjoint? So let's express the event A as the union of two disjoint sets. So that would be A, B complement and AB. So I can write the probability of A as the sum of these two probabilities that you see on the screen, and likewise I can express the probability of B as a sum of two probabilities as well. Now I can sum these two lines, and after just rearranging I come up with the probability of A union B when they are not necessarily disjoint. Now this can be easily extended to the union of three events A, B and C, and you can see a pattern emerging that I first add all the first order probabilities, then I subtract the second order joint probabilities, and then I add the third order probability, and so on. So that gives me, in the case of the union of n events, the inclusion exclusion formula. So I go through all orders of joint probabilities until I complete them. Now, is there a way to express the intersection probabilities in some convenient manner? For that, let us define the conditional probability. In some sense, the conditional probability is restricting the sample space. So what is the probability of A given that B has occurred? So it's defined as the ratio of P of A intersection B and P of B. So that lets me to express the probability of the joint event AB as the product of one conditional and one marginal. This can be generalized to in the case of n events, like in a chain that you see on the screen, as the product of conditional probabilities all the way up to P of A1. Now, one point to note is that when we reduce the sample space this way, all the known rules still hold. So if P of A complement is 1 minus P of A, then when I restrict the sample space to X, so P of A complement given X would still be 1 minus P of A given X. And likewise, P of A union B given X would still be P of A given X plus P of B given X minus P of AB given X. Let's move on now to the concept of statistical independence. Now, independence is a rather delicate concept. Two events are said to be independent if they are not related in any way, neither causative nor associative. Now, often this assertion of independence between two events is made from experience and heuristic reasoning, and not so much from rigorous proof. So in many cases it's more a statement of faith. Now, two events are said to be statistically or stochastically independent if and only if the probability of occurrence or non-occurrence of one is not affected by the knowledge of occurrence or non-occurrence of the other. So this is the symbol we use. So if A and B are statistically independent, then the necessary and sufficient condition is P of A given B is equal to P of A. And I could write equivalent statements which you see. So in the end, P of A intersection B is the product of PA and PB. When I have complementary events, for example, these would all hold. So all these equations would hold equally well when A is replaced by A complement or B is replaced by B complement. When I extend this to the mutual independence of n events, so the probability of the joint probability of any subset of them must be the product of the individual probabilities. And as in the case of A and B, this would hold if I replace any of these A's with its complement. Now let's move on to the theorem of total probability. We have partitioned the sample space into B1, B2 up to Bn. So the B's are collectively exhaustive and mutually exclusive. So I can define a new event A on the sample space, and for any such set A, I can describe it as the union of its intersection with all the individual B's. And because these intersections are disjoint, I can conveniently express the probability of A as the sum of all the intersection probabilities. Now this I can expand. I can expand each of the joint probabilities A, Bi using the conditional. So P of A, Bi is P of A given Bi times P of Bi. So this is a more familiar expression of the theorem of total probability. This takes me to the Bayes theorem. So suppose I have the same partition of the sample space, B1 through Bn, and suppose some new knowledge, which I call K1, has been obtained, and say these B's are some original hypothesis. So with this new knowledge, can I update the probability of one of these, say Br? It turns out that I can do it by simply restating the definition of the conditional probability. So I can express P of Br given K1 as the original P of Br times the probability that K1 would occur if Br is true, and normalized by the probability of K1. So this is basically stating that the updated probability of Br with the new knowledge K1 is proportional to the likelihood of that knowledge and the original probability of Br. A more familiar expression of Bayes' theorem is what you see now, where the denominator is expanded with the help of the theorem of total probability. Now, if new knowledge keeps coming in, K1, K2, and so on, sequential updating of PBR is straightforward.